everybody. Welcome. This is going to be lesson 1.7.12. This is going to be part one about talking about exponential, reasoning about exponential graphs. So a big thing we're going to be looking at is how the equation affects how the graph looks. Mainly like how curvy the exponential curve will be. And how high it will be on the graph, how high or low. So that's kind of our main focus for today. So if you haven't already, go ahead and join at joinpd.com. MDPXB is our code. And if you come in late, it will be above me. You can still join in after I move away from this screen. All right. So, once again, this is reasoning about exponential graphs, part one. Okay, so here is our warm-up. So this warm-up has 4 choices. So here, Jada received a gift of $180. In the first week, she spent a third of the money. She continues spending a third of which is left each week thereafter. Which equation best represents the amount of money in dollars she has after T weeks? Be prepared to explain your reasoning. So this one is just going to be a poll so I can get a sense of what you believe is the correct answer. So here are our 4 equations. You'll be picking which equation you believe matches the best. So we have g equals 180 minus 1 over 3 times t. Equation 2 is g equals 180 times 1 over 3 to the power of t. G equals 1 over 3 times 180 to the power of t. And then g equals 180 times 2 over 3. Okay, so just go ahead which equation you believe fits this situation. And I'll be showing the poll of what we believe to be the correct answer. Okay. All right. So I'm going to go ahead and show some of our responses to this. Okay. All right. So it looks like 1 thinks equation 1, 3 of us think equation 2, and then 2 of us think equation 4. So let's take a look at these choices that you pick. So first of all, so the first one has a minus. So losing, subtracting by 1/3 each week. So this would be saying like if you started with $180 and then you would subtract 1/3, which is maybe 1/3, I believe, is like 33 cents. Okay, so if you were to subtract 1/3 each week, that would be saying she's losing about 33 cents each week. So the first equation would be, okay, I'm losing 33 cents each week. Okay, so I can see now that someone switched away from equation 1, seeing how we're not really subtracting 33 cents every week. What we wanted was a third of our money. And that key thing, a third of means multiplication, so we know it's going to be one of these 3. Okay. So now we have these 2 equations. So you guys did a good job realizing that our initial value is the number that does not have a variable. So nobody picked equation 3. So you guys did a good job with that. So then the big question is, so now we have 4 on equation 2 and 3 for equation 4. So which of these 2 is going to be correct? So we have to see what the words are saying about this 1/3. So she continues spending a third of what is left each week thereafter. Okay, so that means she's losing a third each week, which means there's 2/3 remaining. Okay, so if she loses 1/3 of 180 each week, that means that there's going to be 2/3 of 180 remaining. Okay, and when we're writing equations, So if she's losing a third of 180 one week, that means there's going to be 2/3 remaining. So the key thing here is when we're writing our equations, we want what's remaining. That is what our equation calculates. So this factor here needs to be not what she's losing each week, but what's remaining. Okay, so she's spending a third of 180. Okay, so she's spending a third of her money each week. That means there's 2/3 of her money left. There's 2/3 of her money remaining. Okay, so the correct answer for this one is going to be 4. Okay. So again, if she's losing a third of 180 every week, that means there's 2/3 remaining. And you can see that because 1/3 plus 2/3 gives us our 3/3, which is the same as 1. Okay, so if she's losing 1/3, that means 2/3 is remaining every week. Okay, so when we write these equations, make sure that your rate, your growth rate here, is calculating what remains, because we want to know how much money she has left each week. I don't want to know how much she spent. I'm interested in the amount of money she has remaining. So that's why we use the remaining factor when we're doing these calculations. All right. So what we're going to be looking at is more of graphs. Okay. So each of the following functions, f, g, h, and j, okay, which are over here, represent the amount of money in the bank in dollars as a function of time, x, and years. They are each written in the form m of x equals a times b to the power of x. Okay, so what we're interested in is the b value. So here's our equation, okay? And if you notice in our equations, all of the a's are the same. What is changing is our b values. So our rate of change, or our b value right here, is what's changing with these graphs. So what we want to know is, how does the b value affect in our equation affect how our graph looks? Okay, so and I'm going to color code it so you know. So this equation is going to be the red one, the red line. Okay. Equation G is our blue, right here is our blue line. Okay. Equation H is our green line. So this is our H. Okay, and then equation J is our purple. This one here is J, our purple line. Okay, so we have equation equation F, G, H, and J. And once again, what you are going to be doing, I want you to explain, how does the b value, how does this highlighted part, the rate, the growth factor, or the decay factor, how does this affect the way our graph looks? All right, so I'm going to show some of our responses. All right, so let's take a look at the one at the top here. Okay, as the factor decreases and gets to 1, the closer the line gets to 0. And if the factor is less than 1, the graph decreases to the right. Okay, so it looks like what the student is saying here is that if this growth factor is less than 1, okay, so 0.5, 1 over 2, is definitely less than 1. And anything less than 1 is going to be decreasing. So J seems to be this only one that's going in the other direction, and that's because the B value is less than 1. Okay, so that's a good observation for function J, that B is less than 1, so it's going in this direction. Okay, so then let's take a look at this. F is doubling and G is tripling. Good, so if we look at F, it seems to be doubling, okay, because of this 2 here, and then G seems to be tripling, right? So if F is doubling and then G is tripling, what are we noticing about these graphs here? Like, what's going on? Okay, so the B value is changing because some of the numbers are negative and aren't the same. Okay, so none of these numbers are negative, however, some are less than 1. Less than 1 doesn't necessarily mean negative. Less than 0 means negative. So instead of saying negative, we'd want to say that they're less than 1. But yeah, so all of these B values are different, and we see that these graphs definitely look different. Okay. So J is on a different direction. Okay, so we know so that because when things are less than 1, it's going to go in a different way. Okay, so then let's talk about the heights here. Okay, so H is our highest. It seems to be higher than the other ones here at the curve. And then F, it's like, so it's like, what is making these like what's making these do that? Why is HFG kind of layered like this? Okay, and so if we take a height, if we take a look at like when all these graphs reach 10, okay, H is going to be the slowest to reach 10. Okay, so all right, so okay, so sorry, H is going to be so here it's got the biggest, this is the biggest negative number, right? So here the H reaching is reaching 10 when the negative is the biggest. Okay. Here F is reaching 10 when the negative is a little smaller, and then G is reaching 10 when the negative is the biggest value. Okay, so we could say okay, so what is happening here? Why is that happening? So if we take a look, if we look at the actual rates, okay, so H, the rate is 3 over 2, which is 1.5, is the growth factor. F has has 2 as its growth factor, and then G has 3 as its growth factor. Okay. So, as we'll see that this this graph here, okay, it seems to be rising. It looks to be a little higher than these other ones here. Okay. So, if we look at these, because we know that F is supposed to be growing faster because 2 is bigger than 1 over 1.5. And we know G is supposed to be growing faster than 2 because when you triple something, it's going to grow a lot faster than 2. So if we take a look here, so if I take this function and I change this to 3, and then I change this one to 1.5. Okay, so what's interesting here is you're going to see this kind of flip. Okay, so the blue one, okay, the blue line, it starts below and then it goes over, okay, because we know that the blue one is supposed to be the fastest, right? So the blue one, it's going to be growing faster than the other two, so it goes on top. Okay. However, in the negatives, it's growing the slowest. Okay. So when the growth rate is a big number, when we look in the negatives, okay, it's going to be the slowest. However, once we get to the positives, it's going to be the fastest. Okay. So here for red, it stays kind of in the middle. It's the second fastest and the second slowest both times. And then this one here, the 1.5, okay, so this one it seems to grow faster in the negatives, but then it grows slower in the positives. Okay. So depending on how big the B value is when we're looking at positives, okay, it'll be the top graph in the positives, but it'll be the smallest in the negatives. And that's because a -3, right? Negatives, so when we are actually 1 over 3 is smaller than 1 over 2, which is smaller than 2 over 3, okay? However, 3 is bigger than 2, and 2 is bigger than 1.5. Okay, so when we are looking in the negative ones, the biggest growth rate here is actually going to be growing the smallest. But when we look in the positives, it's going to be growing the fastest. Okay. So if an exponential starts in the negatives, it's going to be the slowest growing. Um, but then when we get to the positives, it's going to become the fastest. Okay, because as we can see here, it takes longer to reach 10 for G than it is for H. However, for here, it's faster for G to hit 100 than it is for F and for H. Okay, all right. So moving along here, okay, so this is a different graph. This time the rates are all the same, however, our starting value are changing. So let's take a look at how this affects our graph. So for this one, as you can see that what's the rate of change are all the same. However, what's changing here is the starting value. Okay, so how does changing our starting value affect our graph? Okay, so if we look at these graphs, so when we change the starting value but the rate is the same, these all have the same shape. Okay, so these lines, unlike the other one, they're not going to intersect. Okay, so these lines, because they are growing at the same rate, they don't cross at all. Okay, but what we see is that their starting value on 0 are all different. Okay, so where they start, it's going to be all different. However, these are never going to cross. If we look at our previous graph where the starting value was all the same, they all start at 50. However, their growth rates change the shape and how much the graph will curve. So like once again, so when we changed the rate, it changed how the curve looked. Some were more flat, some were more curved, and they all intersected at the same starting point. Okay. However, if we give them the same rate and different starting points, these lines are never going to intersect. Okay. And the shape of them stay the same. It's just they're a little bit more to the left. Okay. So what it does when you keep the rate the same but you change the starting value, okay, they're gonna shift the graph left. Okay, so the higher the number, the more left it's going to be. So the higher the start, the higher the starting value, the more to the left your graph is going to be. So the higher the starting value, okay, the more left it will be. And this is, and just to see if this is always true for all, if we had a negative, okay, or sorry, if we had a fraction. So let's change these to decimals. Okay. So if it was a decimal, the lower the starting value, the more left it's going to be. Okay. So so if the rate is positive, the higher the starting value, the more left it would be. However, if the rate is negative, the higher the starting value, the more right it will be. Sorry, not negative, but if it's less than 1, that's what I mean. So if the rate is less than 1, the more to the right it will be. If the rate is positive, if the rate is greater than 1, I should say, the more left it would be. So if the rate is greater than 1, as we see here with 4, the higher the starting value, the more left it's going to be. Okay. If the rate is less than 1, as we see here, the higher the starting value, the more to the right it's going to be. Okay, so it kind of flips in that way. Okay. So the starting value is shifting. The moral of the story is that the starting value is shifting the graph left and right. Okay, so when we change that starting value, it's going to shift our graph left and right. When we change our rate of change, it's like the graphs will start left, and then these are different shapes. Okay, so the shape of our graph is going to change if we change our rate of change. Okay, the position of our graph is going to change if our rates are all the same, but we're changing our starting value. Okay, so the starting value affects the position of the graph. Okay, the rate of change affects the shape. Okay, so the starting value changes where it is left and right. Changing the rate will change the shape of the graph. All right. Okay. So to summarize that, on the graph, where do you see the A? Okay. So the A is going to be our y-intercept, our starting value. Okay, so where we see A, this is going to be our starting value. And for this one, the starting values are all at 50. Okay, so the A value is going to be our starting value. So this is the, which is the y-intercept. Okay, and how does this the size affect the graph? It shifts the graph left or right. Shifts the curve left and right. So on the graph, where do you see the b value? Okay. So is our b value is going from one point to another. Okay. So our b value is our rate of change from our y values. Okay. So this is so the b is going to be our rate of change, which you find by dividing. You would find the rate of change on a graph by taking y2 divided by y1. Okay. So how does this affect the size of the graph? Okay, so this is going to change the shape. So it changes the shape of our curve. So when we're changing our rate of change, we can see that our shape, how fast it's moving in the beginning and end is going to change. Okay, how is J different than the other graphs? As you've stated before, J is different because it is the only one that has a value less than 1, so it is decreasing. So this has a b value that is less than 1, which makes this a decreasing curve. It's going to go in the other direction. Okay, so how is the b value different? Once again, it's less than 1. So this goes to the right. And I should say goes down to the right, because they're all going right. All right. So changing the a value in this function, and once again, so changing the starting point moves it left and right. Changing the b value is going to change our overall shape, or how fast it's growing, the overall speed of the curve. All right. This is again going to be a multiple choice for you to choose from. Okay, so suppose you are presented with four functions, m, n, p, and q, that describe the amount of money in dollars in a bank account as a function of time, x, and years. If the account is yours, the more money the better, right? So which function would you choose? Okay, so here are our options for our functions. We have m, which is the first equation, which we have 200 times 1 over 4 to the power of x. We have n to the power of x equals 200 times 1 over 2. We have p to the power of p of x equals 200 times 1 over 3 over 4 to the power of x, and then q x equals 200 times 7 over 8 to the power of x. Okay. And this is equation 1, equation 2, equation 3, and equation 4. So if this was your bank account and your money, which would be the best option for you? Okay, and just so you know, think about, okay, are these increasing? Are they decreasing? And how fast are they increasing or decreasing? Because you want your money to last a longer time. I guess this isn't a multiple choice, but type in your answer, please. And then explain why. All right, so I'm gonna take a look at some of our responses. This one's kind of funny. I would choose the first equation because it's the only one with m and m equals money. Then this student here was for the first, should we multiply by 1 over 4 or 3 over 4? Well, like, which is going to be better, right? That's a good question. I would want the rate with faster, okay? So yes, these are all decreasing, okay, but you want your money to last longest. So which would be the best account? So even though they're all decreasing, you want your money to last the longest. So what would be the best for that where your money would last the longest? Which of these is going to decay at the slowest rate? So your money will last longer. Okay, so someone said I would want 7 over 8 because that is the amount remaining each time. Okay, very good. So if 7/8 of your money remains, okay, that is much better than only half of your money remaining or only a quarter of your money remaining. Okay, so 7/8, this is the biggest number. Okay, so this is going to have the most of your money remaining over time. Okay, so if I wanted my money to remain, I would definitely want to pick the one here. Okay, because I want my money to remain. Okay, so because we start out with 200, I want a lot of my money remaining each week. I do not want my money remaining to be a small amount. Okay, so 4 would be the best, so I have the most amount of the most fraction of my money remaining over time. So let's take a look at some graphs. So we're going to still look at these equations, okay? But we're going to try and see if we can match them. Okay, so we know that we want to figure out which of these is going to have the most amount of money remaining as time goes on. Okay, and so what we're learning about rates of change, and if we have the same starting value, that this rate of change is going to affect how fast or how small my money, how quickly my money increases or decreases. So what you can do is this is graph A, B, C, and D. I want you to match the graph with the correct equation. Okay. So in the tools, you can either type the answer in. You should be able to make your drawing smaller. So let's see this here. Interesting. Okay. All right, so I'm seeing two answers here. So I'm seeing A, B, C, and D, but I'm also seeing A, B, C, and D. Okay? So, which are these are correct? So, so the function that's decaying the most quickly, we know is function d here. So this one is decaying at the fastest rate. Okay, so um, the closer a fraction is to 0, the faster it's going to decay. The closer it is to 1, the closer it's going to be to a straight line. So the slower it's going to decay because the amount that's remaining is close to 1. So the correct answer here, okay, and so you guys did so the students here you did a good job, and here as well. Okay, it is going to be DCBA. Okay, so good job. So this is indeed the fastest decaying one is going to be when the rate's the smallest. Okay, and the one that decays the slowest is going to be the one with the value closest to 1. Okay, so the closer to 0, okay, and again, this is this is only true when the rate is less than 1. When the rate is less than 1 is what we're talking about in particular. So the closer to 0, the faster it's going to drop. Okay, but the closer it is to 1, the slower it's going to drop. Okay. So, and we know this because we know that this is the amount remaining each time. Okay, so that means after 2 weeks, we want the most amount remaining in our bank account. Okay, after 2 weeks, I still want to have $150. I don't want to, after only 2 weeks, suddenly drop all the way like to less than like about $10. Okay, that's way too little of my money left. Okay, so after 1 week, okay, here I have 175 still. Here I would only have 150 from my original 200 left. Here I would have 100 of my original 200 left. And then here I would have only $50. It only took 1 week to spend all that money and only have $50 remaining. Okay, so um, this this is how much remains after each week. So the bigger the fraction, the closer it is to 1, the slower it's going to decay. Okay. However, the faster, the smaller it is, the closer it is to 0, the faster it's going to decay. Okay. And that's somewhat, it's the opposite for the positives, right? However, we did see that even when we had a rate of change of 3 to the x, this one was the slowest to grow when it was in the negative section, right? So, whenever we're looking at these the curves down here, okay, the curves before or after the initial value, the larger value is going to be decreasing the slowest, at the slowest rate. All right. So, I want you to pick 3 different positive numbers. Okay, so because what we're going to do, we're going to take a look at them. We're going to take a look at these graphs, and we're going to really summarize and understand how changing the B will work. Okay, so I'm going to show some responses. So I see 3. So 3 is going to be one of our positive numbers. I'm going to need 2 more positive numbers from you. Okay, there's 4. And then one last positive number, 5. Oh, look, you both picked 5. Okay. All right. So, these are our numbers we're going to have, 3, 4, and 5. Okay, so if B is 2, how would these 3 numbers in place of A affect the graph? Okay, so let's take a look at that. So, let's say 3, and we're saying that our growth rate is always going to be 2. Okay, so here we have 3, we have 4, and we have 5. And our B value here is going to stay the same. So B is going to be 2. All right, so I'm going to zoom this in a little bit so we can see it better. All right, so if our starting value, let's go to 10. Let's say -5 as our window, 5. All right. Okay. So, what does changing if the rates are all the same, how does our starting value affect? So, the starting value is going to affect the height and position of our graph. So, because we picked, because 2 is a positive number, okay, so this is going to affect the height of our graph, and later on, it will affect whether it's further to the left and further to the right, okay? So, how these affect our graph, so changing these 3 different A that you picked, how it's going to change the height. Okay, so the larger the number, the higher up it's going to be. So the larger the number, the higher up it's going to be. Okay, so our y, this is really our y-intercept. It's going to be higher. Okay? All right. So then now it's saying, okay, so if B was a positive number, the larger number, the higher it's going to be. So now it says, okay, what if B instead was 1/2? So let's change our rate to a decimal and see what happens. So I'm just going to change this to 0.5, 0.5, and then 0.5. All right. So here we see it's still going to be higher. However, now this graph, the highest number is going to be further to the right. Okay. So the largest A, okay, which is these numbers that we picked here, it's going to be most right. As we can see here, the one with a 5 is the furthest to the right. The one with the 3 is the furthest to the left. Okay. And if we go back to when our rate was greater than, was not a fraction, not a decimal, it looked like the largest number was most left. Okay, so the largest number is always going to be the highest. However, when we start looking at it over here, if we're talking about a rate of change that is greater than 1, it's going to be most left, okay, because 2 is greater than 1. However, when we're talking about 1/2, which is less than 1, um, this black line here, you're going to see it move and be the one that's to the most to the right. Okay, so when our rate of change is less than 1, okay, the largest starting value is going to make our graph most to the right. When the rate of change is greater than 1, our starting value is going to be, our largest number, our 5, our black line here, is going to be the most to the left, as we see here. Okay? All right. So then lastly, we'll take a look at our cooldown. Okay, this one's a multiple choice. This one really is a multiple choice. So again, this is going to be a somewhat of a which equation is best. Okay, so here are 3 graphs representing 3 exponential functions f, g, and h. The functions f and h are f of x equals 10 times 2 to the power of x, and h of x equals 20 times 4 to the power of x. Which of the following could define function g? Okay. So h is our green graph here. F is our red one. Okay. So the question is, which of these equations would best represent our blue given the information we have about f and h? Okay. Okay, and so this one is a poll. So I'll show you your thoughts in a moment. Give you a little bit more chance to pick some options. All right. So far it seems that one of us picked equation 2, a few are picking equation 3. So let's take a look. So first of all, we notice here that these share an intersection point. These share a y-intercept. So if these share a y-intercept, if I look at h's y-intercept is 20. So you guys did a good job of recognizing that 20 has to be the y-intercept of g, okay, because they share that same y-intercept. All right, so that means that it's definitely not going to be equation 3. Okay, so it seems like we're a little tossed up between 2 and 4. So if we take a look, we say, okay, this is increasing, this rate is positive. Okay, so which is going to be faster? Is h or g going to be faster? Okay, now h is on top of g, so we know that h is going to be faster than g. Okay, so if h is faster than g, that means G, the rate, has to be less than G. So H has a rate of 4. Okay. Now, because these are positives, okay, so and then this one is H here, and then G is over here, right? So H in the negatives, we see that it's slower, and in the positives, it's faster. G in the negatives is faster, in the positives, it's slower. So that means G's rate has to be less than 4. Okay. So this actually cannot be equation 4. Okay, because 4.5 is faster than 4, but G is rising slower. Okay, so these start at the same place. However, H is going a lot faster than G is. It's rising quicker. It gets to this point before G does. Okay, so it can't be equation 4. So that leaves these two. Okay. So then we have to compare G to F. Okay, so which one could represent G? Okay. So it is actually, you are correct. It is going to be equation 2. Okay. So 1.5 is a little too slow because we see that G is growing at a pretty similar rate to F. F is growing at a rate of 2. Okay, but this one seems to be going a little bit faster because you can see the steepness here. The steepness of F is less steep than G is. Okay, so that means G is going slightly faster than F. If F is going at 2, G should be going at 2.5. So the correct answer for this one, it actually is equation 2. So good job for those of you who picked it. Just keep in mind the key things to know is that when we're in the positives, the higher it is, if they have the same interception point, the higher graph is going to be faster. So H is faster. And then the steepness tells us about our growth rate as well. And we can see here that G is slightly more steep than F is. So this is 2. This one's going to be a little bit faster than F because steepness, as we know from lines, indicates the speed, the rate of change. Okay. So this was just part 1 of using graphs to understand, looking at the equations in the graph. So if it's a little bit confusing, don't worry. Next week we're going to do part 2, and hopefully it'll clear up a lot of things. Okay. So thank you for participating. I really appreciate it, and I'll see you next time.